Here we've got a problem that says that Bart kicked a football. The height of the football is given by the height function. H of t equals 80t minus 16t squared. T is the time in seconds since the football was kicked, and the height is measured in feet. So this time, we're not using meters, we're using feet. So our input is t, still seconds. And our output, h of t, is the height in feet. We're going to put this equation into our graphing calculator for y1. And we're going to answer the questions using our calculator. So I'm going to go over to my calculator. If you need to press pause, go ahead and do that and put the equation into your calculator. Just like that. Now, when I hit draw, I had a standard window, so I'd like you to make sure that you have a standard window so that we can adjust the window together. I press enter to draw the graph, and I see that I've got x-intercepts. It looks like there might be one at x equals 0, and then maybe again at 1, 2, 3, 4, 5. So I'm going to change my window. I know I can't have negative time, and my x values, which are your inputs, are representing time. So we can't go back in time. So I'm going to make that a 0. However, I do like to see a little bit to the left, so I'm going to make it -1. And then I counted over 5 seconds for it to hit the ground, so I'm going to make the max a 6. And I'm going to press enter. And you can see I've got a little bit to the left, which is just kind of like the frame on the picture that you want. You've just got a little bit of a frame to the left and a little bit of a frame to the right. However, I can't see the Y values. I can't see where this turns. So I'm going to hit zoom auto. Now that I've adjusted the Windows domain, I'm going to hit zoom auto, and it fixes the range for me. So the football is starting at a height of 0. It's gonna come up to a maximum that looks like it might be about 100, maybe 100 feet, and then it's gonna fall back down to the ground. This part of the graph is the only part of the graph that works for this problem, because this part of the graph doesn't really exist because you can't go back in time, and you can't have negative height. Same thing here. Once the ball hits the ground, the play is over, right? Once the ball hits the ground, the play is over. This problem is over because the ball can't have negative height. It doesn't keep going down to the center of the earth. So now that we know we're just dealing with the parabola above the x-axis, we can answer the questions. So the first question says, what is the height of the ball at its highest point? So here, what I'm hoping you did was you hit G solve, and I'll write this down. What you should have hit was G solve, and then max. Now you can do that once you adjust the window. So if you did not adjust the window, you need to make sure that you adjust that window. Otherwise, you might not be able to get the answers. The maximum height is 100 feet, and that occurs 2.5 seconds after the ball is kicked. So what's the height of the ball at its maximum point? 100 feet. It's the Y value of the location of that maximum. And how many seconds does it take to get to that highest point? That's going to be the X value, which was 2.5 seconds. And how many seconds does it take till it hits the ground? This part right here, I'm gonna draw you a nice little graph. It was 0, 0, it went up to a maximum, and then it went down here. So between these x-intercepts, so the distance from one x-intercept to the next x-intercept, those are the roots. And you're going to go into the calculate let's see what you're gonna do. Let's show you what you're gonna do. You're gonna go to G-solve. So G-solve root. The one on the left is x equals 0, and the one on the right is x equals 5. So you're gonna calculate this. This is 0 and this is 5. You're gonna calculate by subtracting 5 minus 0, which would be 5. The x-axis stands for seconds. So how long until it hits the ground? It would take 5 seconds after it was kicked for it to fall back down to the ground. Now that was pretty quick, so we're gonna do one more here. Raul kicks a soccer ball towards the goal. The graph below shows the height in feet of the ball over time in seconds expressed by the function f of t equals negative t squared plus 9t. I'm going to write that a little bit bigger so I can see it. F of t equals negative t squared plus 9t. We want to know the average rate of change. So this is something new. The average rate of change is just the slope between 2 points. So the average rate of change is the slope between 2 points. And those 2 points are going to have x values that are dependent on the interval. So over the interval from 1 to 4. So here's 1 and here's 4. So we got a 1 for an x value and a 4 for the x value. So these right here, x1, x2. Now we need to find the corresponding y values. When you put a 1 in, we're going to get an 8 out. So I go over to my graph, I put a 1 in, I get an 8 out. That ordered pair is 1, 8. That's going to be my ordered pair to calculate the slope between 2 points. The next ordered pair is 4, 20. That's the second ordered pair. And then the slope between 2 points is your change in y, your change in y over your change in x. Change in x. So the change in y goes from 8 to 20. That change in y is going to be 12, and it's labeled 12, I believe, feet. Yeah, 12 feet. So the change in y is 12 feet. I don't like the way I wrote that. Let's write it a little bit neater. 12 feet. And the change in x is going to be 3 seconds. So 8 to 20 is a change of positive 12, and 1 to 4 is a change of positive 3. So there's my 3 seconds. 12 feet over 3 seconds is the same thing as 4 feet over 1 second. So 4 feet per second is going to be our average rate of change. And that would be answer C, 4 feet per second. Now let me show you on the graph how we can do that rise over run. So slope is equal to rise over run. And I always start at the point on the left, so I'm always either going up and then down, or up or down, and then always moving to the right. So if I'm always moving to the right, my run is always going to be positive. So going up would be a positive change in y, and we go up from 8 to 20, so that would be 2, 4, 6, 8, 10, 12. So up 12, and then we're going to go to the right moving to the right is a positive number. Moving to the right, 1, 2, 3 seconds. So positive 3. So 12 over 3. We've got 12 over 3 is equal to 4. And then remember, our rise was our feet, and our run, which is horizontal, was our seconds. So that would be 4 feet per second, which is still answer letter C. So that's how we find average rate of change, and we'll be working on average rate of change with lots of different functions. So we'll get some more practice with that. In fact, why don't you try number 11? Try number 11, and then come on back and check your answer. Okay, for those of you who didn't press pause and you're still working, I'm not working this out. I'm just going to give you the answer here. So press pause if you haven't quite gotten that answer yet. If you're still with me, that means you just need to know, did you get it right? And if you got 30 meters per second, you got this answer right. Now I'm going to show you the work that goes along with it. So you should have had, this is your x1 and this is an x2 in your interval 1 to 3. So I create 2 x values. Now I need to find the corresponding y values. The corresponding y values, when you put a 1 in, I got a 40 out. And when I put a 3 in, I got a 100 out. That's a change of positive 60 over a change of positive 2. 60 divided by 2 is where this 30 is coming from. And then why is it meters per second? Because your change in y, I believe it's meters. Yes, it is. It's labeled as meters right here. Height in meters over your change in x, which is seconds. So that's where your meters per second come from. Meters per second. And 60 over 2 is 30. Okay, our last video is going to address Alfred hitting a golf ball towards the green. There's an equation for us. What's the average rate of change, and what's the domain and range of the function? So you can go ahead and give that a try. And in the next video, I'm going to provide the answer for you. But if you are comfortable working a little bit ahead and trying some of these on your own, then we're making some really good progress with our word problems.